Hello and welcome to this video where I'm going to talk about logistic regression, especially about how this regression works. And the key of it is a function called the sigmoid function. So that would be the focus on this video. So let's start. Let's start with an example. Suppose we have a binary classification problem where we have to classify whether a student will pass or fail the exam based on his or her study hour. And each dot here is a student, is an instance of a student. So for example, this student, he or she studied for little bit less than 6 hours, and then the result for that student is fail because the label here in the y-axis is 0. Another student here, let's say I picked this one. That student studied a little bit more than 7 hours and the result is pass. Okay, so in y-axis 0 means fail and then 1 means pass. So now if you recall the linear regression, we have to fit these data points with a straight line. But here the straight line doesn't seem very suitable for these types of data points, right? Because what kind of line that would fit this dots nicely, okay? If you draw that kind of point, it looks weird. If you also draw a straight line here, it doesn't say anything about the relationship between the study hour and whether a student will pass or fail the exam. Okay, so linear regression with a straight line fitting these points does not seem suitable. And that's why we're going to look at another type of regression, which is called the logistic regression. So as I said before, and as you've learned in the linear regression videos, a linear regression model tries to find the best line that will fit all the data points or all the dots here. Okay. However, in logistic regression, you see that here that we do not have a straight line. Instead, we have kind of like an S curve here. So this would fit better than a straight line when we have the example of like the previous example about the students who studied very few hours, they tend to fail. And then those who studied with more hours, they tend to pass the exam. So this type of S curve can fit nicely to that kind of data compared to if we draw a straight line like using this linear regression here. Okay. Another thing other than the shape of the line, it is also important to notice that um, the range of y or the range of the dependent variable is different. In the linear regression here, the y-axis can practically can take any value in the with the real value. So it means it can be 0, it can be positive, negative, whatever. But in the logistic regression, the range of the y-axis here is just between 0 and 1. Again, this will fit nicely if we have a binary classification problem where, for example, 0 is the label for those who fail the exam, and then 1 is the label for those who pass the exam. Okay, so first the curve will fit nicely to the data points, and then in the y-axis, the value here also are suitable for describing the labels. Okay, so let's go on further into logistic regression. The S-curve that we saw in the previous slide is called a sigmoid function. First, let us recall our problem, which is a binary classification problem. Given an observation X, or we can also say that this is a data instance, we want to know that given that data instance, what is the probability that that instance will have the label 1? Also, what is the probability given that instance? It will be labeled as 0. So in the previous example, we will say that given a student mentioned that he or she studied how many hours, we would like to predict whether that student will pass the exam or fail the exam. Okay, so that is the meaning of these two notations here. Logistic regression learns the weight for each feature, Wi, and a bias term or a constant b. And then for each feature, we will multiply it with the corresponding weight. In the previous example, we only have one feature, which is the number of hours that a student studies. But in general, we may have n features. So we have xi times wi, okay, for every I features. And then at the end, we will add it with the constant or the bias term. So this can be simplified as z equals to wx plus b. Again, this simply says that for each feature we have the weight, and then we will multiply it, and then finally we will add the bias term. If you notice up to here, z can take the value of a real number. It can be positive, it can be negative, it can be zero, it can be whatever, right? Because the value of each features x here can take a real number. The weight also can take a real number, and the bias can also take a real number. So z is also a real number. And then also you may notice that up to here, it looks the same with linear regression, right? Linear regression is just saying that we have the weight for each independent variable, and then we have also a constant term. So it's exactly the same up to this point. Okay. Now, how logistic regression may change this into the S-shaped form that um, that that is more suitable for the problem that we have in the binary classification problem. The key here is we are going to pass this z value, which can take a real number, into a function that is called a sigmoid function. And the sigmoid function looks like this. Okay, so the function says whenever you have any value here, z, and then we're going to pass it to this function 1 over 1 plus e to the power of minus z. So as the result, after you passing any real number to this function, we will have the result here. Y will be value in the interval of 0 and 1. Okay. Now, if you think about this range between 0 and 1, we can also say that the interpretation of this range is a probability. And by that, we are able to answer this. What is the probability of that instance is labeled as 1, and the probability of that instance is labeled as 0. Okay? So if I summarize this, we will have weight for each feature, and then we will multiply them, plus the bias term, and then the result, we will put it into a sigmoid function. So the very final result will be a value between 0 and 1. So this is how a sigmoid function looks like, which means that whatever z value that you pass into this function, the result will never exceed 1, and it will never be less than 0. And we may interpret this result in the context of binary classification problem is the probability that the instance that we have is predicted to have the label 1. So in logistic regression, we will multiply each feature with the corresponding weight, take the sum, and then add the bias term. We obtain z, and then we put the z into the sigmoid function, and then the result will range between 0 and 1. Now we're going to look at the effect of w and b to the shape of the S curve. First, if we change the w and keep the b in a constant value, we will see that the curve becomes steeper when the W gets larger. Okay, so the thicker line here is when I'm using the W equals 1, and the thin line is when I'm using W equals 0.3. You can see that with W equals 1, the S curve becomes much steeper. Okay, when I fix the W, but then I change the B or the constant, the effect would look like this. When B equals 0, we will cross this 0.5 at the when the x-axis is 0. So the x equals 0, and then we will cross y equals 0.5. However, when the b is positive, the curve will go to the left. And then when the b is negative, we will kind of push this curve to the right. Okay, so you see that there is no change in the steepness, but in the position of the curve. So we may conclude that if you change the W, then you control the steepness of the curve, and then changing the B will control the position of the curve, whether you push it to the left from the y-axis or you push it to the right from the away from the y-axis. In the logistic regression model, we're going to use the sigmoid function to produce the output, which can be interpreted as the probability of an example being labeled as 1. Okay, so here the wx plus b, and then you pass it into the sigmoid function. This gives the probability of the label is 1. So in our example, you can say that, let's say if the result is 0.79, it means that with 79% of probability, the student will pass the exam. And then since our problem is a binary classification problem, the probability of the label 0 is just 1 minus uh, this result. Okay, so in our example, you can say that the probability of the same student fail in the exam is 0.21 because our problem is a binary classification problem. So these two probabilities must add up to 1. Okay. Now, these two are probabilities. It is a bit different with our decision. For example, we would like to decide whether we let the student pass or let the student fail based on these probabilities. Usually, people will use or will decide that if the probability of labeled 1 is greater than 0.5, then the decision is 1. We say that he or she passes the exam, and then 0 otherwise. However, it doesn't always have to be 0.5. For example, in a very serious exam or in a very difficult exam, maybe you would like to set the boundary at, let's say, 0.85. So only the students that predicted to have probability of passing greater than 0.85, and then you will say, or maybe you will let them take the exam or something. And then below that, you say they're going to fail anyway, so you do not let them take the exam. Maybe that's your decision. Okay, so what I'm going to say here is that sometimes you have a different decision boundary than the 0.5. Although commonly people will say that when the probability is greater than 0.5, then we will just give the prediction or decision equals 1, or in our example, we're going to say he or she passes the exam. Okay, but remember that that is not always the case. Decision boundary is more like related to the problem itself, and then we may set the suitable decision boundary for our problem. While from the logistic regression, remember that these values, they are just probability, the label is 1, probability the label is 0. Now here's an example for you to try. We have an instance to be classified and it's a binary classification problem. And this instance has 6 features and these are the features here. Okay. And then assume that we have learned the weight for those features are these. So obviously we also have 6 weights because the first weight here is for the first feature and then so on until this 6th weight is for the 6th feature. Suppose we have also learned the bias term equals 0.1. What you need to do is compute the probability of this instance predicted having the label equals 1 and the probability of that instance being predicted having the label equals 0. Remember that this is the formula to calculate the probability of an instance having the label 1. What we're going to do is first we're going to calculate this Wx plus B. Recall that the features are already given in the previous slide, the weights are already given, the B, the bias term has been given as well. So in doing the Wx, what we need to do is we calculate the feature with the corresponding weight. So 3 times 2.5, 2 times minus 5, and so on, and then take the sum of the result. Okay, so it is called a dot product formula. So 2.5 times 3 minus 5 times 2, and then up to the last one is 0.7 times 4.19. And then you take the sum of all these values. And then after you get the sum here, do not forget to add the bias term, which is 0.1. Okay, and then the result is 0.833. Okay, so 0.833 is the Wx plus B here. And then we pass it to the sigmoid function. So we're going to calculate 1 over 1 plus e to the minus 0.833. Okay, and then the result is 0.7. And then for the probability of that instance predicted having the label 0, we can just take 1 minus this 0.7. So the answer is 0.3. Now, what do 0.7 and 0.3 mean? It means that given an instance with these values for the features, our model with these weights and that bias will predict this instance belong to the label equals 1 with the probability of 0.7. So our model says that that instance is more likely to have the label equals 1 with a probability of 70%. And then this same instance has the probability of being labeled as 0, but only with the probability of 30%, according to our model with this weights and this bias. Okay. And then given that the model says, let's say 70% pass, 30% fail, when we decide whether it will pass or fail, remember that we need to have a decision boundary. If our boundary is 50%, then we will decide that this instance will pass. Okay. Otherwise, if we have, let's say our decision boundary is 90%, let's say because the exam is super difficult, then we will say that with the probability just 70%, we think or we decide that this student will fail. Okay, so that concludes this video where you have learned the logistic regression, how it looks like, and then the sigmoid function behind it. You can calculate it given the weights and also the bias. You can calculate whether an instance with the given feature belongs to the label 1 or the label 0. In the next video, we're going to talk about how can we find the best W and the best bias term. Okay, so see you on the next one. Thank you.